m is equal to n minus m minus 1 times Vm if Vm is the mth mode of a vector in the L0 eigenspace of conformal weight n. Now, you can extend this to a little bit further in order to prove that if you take two vectors, v and v prime, so then this expression is always a Laurent series in Z, something I claimed all the time. And so it's probably good to verify that at some point. And what do you do is we write down this field explicitly, so we get corresponding vectors. You compute the L0 eigenvalue of each vector, and you use the property that's erased of a grading restricted VOA, that these eigenspaces vanish if the weight becomes too negative. And that's exactly the condition that makes this a priori power series in Z and Z inverse to truncate to a Laurent series to bound the pole order. Is a formal power series in both variables, and the coefficients are endomorphisms in V. So what can I do is this condition is clearly equivalent to this operator being the zero operator. This means I can write here V3, this equal to 0 for all vectors in my VOA. And that's maybe a little bit nicer to digest than having a formal power series with endomorphisms. So now it becomes that a formal power series in V being 0. Okay, now you can make this even more understandable by adding a fourth vector. So let's think about what do we even like more than a vector space? The complex numbers, maybe just a field. So let's relate this to what can we do is to a vertex algebra one can associate its graded dual. So this means the vertex, this is now not a 1 but a prime. Just the space, yeah, it's called the contragradient dual or the dual of V. And so this means I can take a fourth vector, let me call it V prime in the graded dual, and let V prime apply to it. So the notation is, one takes is the physics notation with such brackets. And then all of a sudden this becomes a statement about formal power series in C. And again, the original locality statement is equivalent to this statement being true for all V3 and V prime, if that holds for all vectors. But this is now a formal power series in C, and I stated this lemma in one of the very first lectures, that a formal power series in C that satisfies this property must be a sum of formal delta distributions and their derivatives. The derivative are going up to order n minus 1. And that's maybe a good way to think about the locality. It's also a way that clearly relates here to the duality statement. So what you can do is a few step procedure to somehow make the statement clear. The locality statement is a statement about vanishing of a formal power series in two variables where the coefficients are endomorphisms. Endomorphisms are act, so I can act, and it becomes a statement about vanishing of formal power series in V. A vector space has a dual space, so I can pair. So then it becomes a statement about formal power series in C. But for formal power series in C, it is known that this condition is equivalent, that this bracket itself can be nothing else but a sum of formal delta distributions, and the derivatives, the order of the derivative going up to n to the negative n minus 1. And now, if we think about it, this fits enormously well with the lemma that we had, where we said that the commutator of two fields can be written as a sum of fields in one variable with coefficients formal delta distributions and their derivatives. Right? And from that expression, in fact, you get this locality back if we take this logic, because we can take the commutator of these fields, pair them with act on a vector, pair with a dual vector, and apply this lemma that tells us that derivatives of formal delta distributions multiplied by a sufficiently high power of z minus w vanishes. So everything somehow nicely closes of what we have seen. Okay, so this is maybe putting everything we had in a common context. Okay, now so I'm spending an enormous amount of time on just vertex algebras itself for an obvious reason. It's not something you can introduce in a few seconds. But the vertex algebras are interesting because of representation theory. So we now want to go there, and we want to continue with logic. I mean, we saw that a vertex algebra is a vector space with the most important structure having fields on them, and the fields satisfying an important axiom called locality, which can be equivalently phrased in this way. And now, what could a module possibly be? It needs to be a vector space on which the vertex algebra somehow acts. That's a module. And how could the action be? It should come somehow from fields again. And the fields should satisfy axioms such that, in particular, the viewer A itself becomes a module for itself. Right? And so that means it should somehow be an axiom that naturally generalizes locality or duality or both of them. So, and in fact, it's yeah, and then there's a third axiom called Jacobi identity, and I wanted to introduce this a little later. The Jacobi identity is totally non-enlightening, so I'm not very keen on it, but it turns out I can prove something really nice once I have stated it. So I thought, why don't I state it in the moment I need it? You see it, we use it immediately, and then, yeah, and that's it. And Jorgen, your task is to stop me so that we get good lunch.
Okay, I'll try.
Yep.
So these I'll just stop you anytime to go to the canteen, and I'll leave the responsibility.
Yeah, that's what I meant. Okay. So modules, and I should write.
You promised to write capitals.
Yeah.
Maybe change the pen.
And maybe, but they are actually, most of them are already.
Maybe once they're bad, throw them in there. I got rid of the terrible pens, so if you use the ones all
Very, very good. Thank you. That gives you get a bonus point. Okay, and it's not.
Okay, I did terrible.
Okay, you get half a bonus point.
Yeah, the ones on the thing I tested, so they're
Yeah.
more likely to be better.
I've already done something.
This one looks quite good.
We do not use the pen technology, right? You spend all our education being educated with black books.
Yeah, absolutely. And
Anyway, just use
Right.
the pen a little bit because it takes a little while before it gets flowing.
I
You
see.
can test the pen
Yeah.
by using it in one line.
Yeah. I'm.
One stroke.
Yeah. Chalk is so much nicer.
Yes.
And by now, classes one is even required to write on an iPad. This is okay. We take V to be a grading restricted VOA. And M a vector superspace. And then we call M a V module. If we have fields, which we denote by Y again, if it's clear that it acts on M, maybe you can forget the subscript, but it's probably good for the moment to add it. And then what could it be? It needs to be V wants to act but on M, so we need to have a map from V to endomorphisms on M. I mean endomorphism valued fields on M. And now with properties, of course, one thing you want it to be is that you want the identity to correspond to the vacuum vector. And one of the two equivalent locality conditions holds. And so one of them is, here now we put it as a condition that the action gives us a Laurent series. And yeah, these are always linear maps. And then we want the old locality property to hold. So we can take the commutator of two fields. So it's the same property as before. For any two given vectors, the commutator of the corresponding fields vanishes if multiplied by a sufficiently high power of z minus w, the power depending on a and b. And then and the third property is that you want the field corresponding to a mode acting on a vector to be related to the normal ordered product. So to the minus n minus first derivative of z of the field and I continue here below. And this one you want to hold for negative n. Okay, so this is clearly very similar, not quite exactly how we defined a VOA, but it resembles the definition of the VOA. In particular, the important property, the locality, is in there. And the second condition, the equivalent one, is the duality condition. So this means it's now, let's see what do we have to change. These are now operators that act on our VOA. So I have to write an index m. And what else do we have to change? V3 is now, V3 is now a vector in our module, of course.
I think you put too many m's.
Hmm?
You have there's ym, the second one's probably not
Absolutely.
You've never said anything about translation, and does T have any axioms?
Good point. Let me think. Yes, it's probably safe to better add also the translation axiom to it.
What is the translation?
And with this property and t, which t acts as a derivative.
It sounds like you're thinking about it each time and saying, yeah, maybe we can add this, maybe we don't. I mean, isn't there sort of a theory package here we just roll out? It must be well known.
I took the definition from Huang's notes, E.G. Huang's note, and he had it without the translation axiom. Without the translation property. But this one definitely holds. And it probably follows from this one, but
it's because you have a graded restricted VOA, and you already made T L minus 1, and L minus 1 has things that are already like L minus 1. You already have a conformal. I caused the confusion. I'm used to having conformal vectors in VOAs.
I'm even more confused after this discussion. What's the outcome of this?
There is a conformal vector. And the ym az axioms apply to it, a being equal to the conformal vector, and then L minus 1 from that conformal vector is the T, so you don't need to add.
Why does it follow any property about the commutator of the derivative? I agree. I can imagine how it might follow this T axiom from this second thing, but it's certainly not apparent to me that it follows.
No, it's definitely not apparent. I simply didn't think about it. So let me just say it definitely must hold, and it's not in the definition, so it follows, but I don't know the proof at the moment. Okay.
Can I just complain? So the second thing over there in the middle, the second line in the middle, is the only way you connect the the structure on M to the structure on V. Right?
Mm-hmm.
But something is missing somewhere.
Now that disappeared because it's not that. This is only ym.
What's your question?
So somewhere the structure on M and the structure on V are connected, and I think it's over there. Because on the left-hand side it's okay. Ym applied to A and B.
Mm-hmm.
So that's of the right form, but the right-hand side is not of the right form. Or no, maybe now it is?
Now it is, I mean, I forgot the M here. Right, this is about the action of, this A and B are in the VOA, right? And so this is in particular about the action of the VOA on itself. And the M I just missed here. And these are, of course, fields on M, they act on M. So here the two are related. And here you see here very explicitly that they are related.
Where?
Because here you don't have an M, right? Because here this is a field acting on V2. So this must be a field of the VOA itself. And here we have it acting on M.
The notes you mentioned, could you maybe send a link to Jane about that? And then Jane can email that link to all of us.
Say it again.
You mentioned some notes from which you took this definition.
And
it might be good to have that reference, and everybody could have a look at that also.
Yeah, definitely, I can do that. Actually, these are. I mean, he gave some lecture notes, and they are quite useful. I also wrote some lecture notes, but they are not publishable yet. Yeah.
Okay, now I have a complaint, sorry. So I agree that in the duality axiom, you have a connection between the structure on V and the structure on M.
Yeah.
But that axiom, I believe, is equivalent to the locality axiom, and I don't see how in that axiom you have a connection between the structure and V and the structure on M. Like, shouldn't they both have the same thing? Because
Yes, there is in G.
what is in G?
G of this thing equals ym1.
Sure, but in the other one,
No, but the other one, what other one?
Yeah.
Yman.
Well, you know, wonder how these two could possibly be equivalent, right?
Yeah.
And this one, of course, it doesn't have any V action in it. And but what will it tell you? It will tell you the relation between H and F. But if you look at this one, this tells you you can make this even a little better, and you can right now you look at this.
New pen.
Yeah.
Just no, don't put it back there. Put it on the table. Else you're going to keep using the same pen. So
Yeah. So well, they don't have a long lifespan. So what you can do? This one looks good. So you
Can you toss me that one that stopped working actually?
sure.
who knows whether it comes back.
So what can we do here? We can take here the field corresponding to A, and now let's see what do we want to look here at Z minus W, right? You already see it, right? So I can look at this expression, and now I can I write down the expansion of this field. Let me still do it, because then we all see it. It's okay. I just need. Let me do it here. So you. And in order to match with this one, let me also call the second variable W and not Z. And now I use the linearity. I forgot a B here. Right, I can just write it in this way, and now I can, for each summand, I can use this property here, right? And then you can work to get this relation. So I have actually the proof in my notes. I wrote it down. It was 3-4 pages. It's quite a lot to do. So it's not that you see that immediately. Okay. Anyway, we have the definition of a module. Now we have always one example, the VOA itself. Would be nice to have a second example that you always have. And indeed, to any V module, so in particular to V itself, you can you can take its graded dual space. It's called the contragradient dual, and then it inherits a module structure from the original module via a certain formula. So let me write it down. So then, if M is a V module, then the graded dual space M a V module and M, here I assume M Z-graded V module, so that means I can write M as a direct sum of eigenspaces of the Virasoro zero mode. Then this dual is a V module as well, and it's defined via the following formula, which one definitely doesn't remember. So we need to define a map called y of m prime. And you define it using, so if we have the dual space, in particular it gives us a pairing between m prime and m. So having this dual space, we have a pairing which is denoted by these cat and bra brackets, and what you define the action of the field corresponding to a vector v on m prime by this formula. You use the action of v on m, but now in order for this to satisfy all these properties, you have to use the Virasoro action as well. So one can prove that this tells us, this defines a V module structure on the dual space. Okay, more general. Let's write down a few examples. The example of a vertex algebra that we have was an affine vertex algebra, and now what can we do? We can construct modules of the affine Lie algebra, and and they are then automatically modules for the universal affine vertex algebra. So example is, let me recall, G is a Lie superalgebra. And then we had the affine vertex algebra VKG. And now let rho be a G module. Then I defined the module that I called VK rho. The formula I wrote down was this one. It's the, let me first write down the expression. So what I do is I take a module for G. I identify G with the, remember the affinization, G hat was the loop algebra of G. That means Laurent, I do base change. I now view G over polynomials in T and T inverse, and I add a central element and a derivation. The central element on the VOA and on any module I require to act by the scalar K. It's always fixed. So, and the derivation I don't care about. So for example, I just let it act as 0. Then rho becomes a module for the constant part of a G hat. Then I act all the positive part, act on rho as 0, and then let the negative part act as freely. So in particular, this module will always have a basis given by a basis of rho times polynomials and then all negative modes. And
what does it mean to raise negative z to the minus 2 to an operator? I understand e to the operator, but I don't know what it means to do.
Yeah. I always assume V to be grading restricted, so it's graded by L0 eigenvalue. So that means it makes a sense on an eigenvector, and every vector is the sum of eigenvectors.
Okay, thank you.
So okay, so this gives me a bunch of modules, and but these are by far not all. Let me maybe continue here with and the action is, it has a natural action of by G hat, and then and the action of the fields are the exact same formula as before. All right. So, for example, you have if you call let me just call this for short M. So then the field, for example, corresponding to the -1 mode, which was always the most important one for some element of the Lie algebra, is given by this formula again. Just now these xn viewed as endomorphisms on M. Yeah? So anyway, the question I asked is, do you think that this vacuum Verma module is a simple module for the affine Lie algebra? You think not? Yeah. So the correct answer is you can't answer it. So it depends on K, right? So what turns out is if you choose K to be a generic complex number, this is a simple module. If you choose it to be a rational number, then it becomes a subtle question. It also depends on what you choose as your bilinear form. So yeah. So now let's be a little bit more specific. So let's specify take G to be a simple Lie algebra, and then B, the bilinear form is then unique up to normalization, and we normalize it in the usual way so that long roots have norm 2. We just have to fix one normalization, and that's a good one. And then it turns out the following is
Norm squared.
norm squared 2, yes, yeah. Norm squared root, yeah, absolutely. And then it turns out that VKG is simple if K not a rational number that is greater or equal to the critical level. The critical level is minus the dual Coxeter number. Dual Coxeter number, for example, for SLN is n. That's always good to remember. Some fixed number. So if the level is in the set, then almost always this one is not simple. You just have a few exceptional boundary points.
Can you please define simple?
Simple as a module for the affine algebra.
Oh, we're not talking about as a module of the Vertex operator.
Yeah, and the two notions are equivalent.
I'm sorry?
And the two are equivalent. So and it's not simple as a module for the affine Lie algebra or equivalently for the affine vertex algebra. So
Sorry, I wanted a definition of what does it mean to be simple for a vertex algebra.
right.
So now
Well, I didn't introduce an ideal, etc. Right, but it's but you can introduce the notion of an ideal. I mean, it's a right. It's a submodule that so such that if you act with a VOA on it, you stay in there, it just has the ideal property. Anyway, for the affine vertex algebra.
I don't understand what's the hesitation to define simple. Simple means no submodule, right?
No submodule, yeah.
No trivial submodule.
Yeah, no trivial submodule, exactly, full stop. So anyway, what I wanted to say is that these vertex algebras, they are almost always simple, and then there's and then everything I said is fine. Whenever a vertex algebra has a proper submodule, then you can quotient by that, and then the quotient inherits a vertex algebra. So. And let me call it V tilde. And in particular, one writes the simple quotient is most interesting. And it gets this a special symbol LK, the K now as a lower index. You'll find different notations. So you write LKG for the simple quotient.
Is it supposed to be clear there's a unique simple quotient?
Hmm?
Is it supposed to be clear that there's a unique simple quotient?
Yeah, I mean, of course, there is a unique simple quotient, yes.
But why?
Why?
Yeah, why?
Well, you have to show that. I mean, that's not totally trivial. Yeah, but there is a unique simple quotent. So
There's still a maximal proper submodule.
there's a maximal proper submodule. You just quotient by that, and you get it.
Why should it exist?
Sure, but
There
there's
is
some
an
grading
explicit
property.
construction of it.
Yeah.
There's some grading type.
Okay. Now the interest. So what's
We should think about.
I know this is I'm already in the process of wrapping up the morning. I just now want to say where we go. So what do you want to do is you want to understand representation theory and you want to give it a nice structure. So if you take the universal affine vertex algebra, so this is the universal one, you don't quotient by anything, then the whole thing is very much like representation theory of the affine Lie algebra, at least in the sense of classifying modules. But you know, a finite dimensional Lie algebra already has an enormous amount of modules and very complicated one. In particular, it has infinite dimensional modules, and they don't have nice tensor products. And so there's no reason to hope that if you look at all possible modules of the universal affine vertex algebra, that you get interesting tensor categories, for example. Now, it is if you pass to a homomorphic image of a vertex algebra, this means you quotient by a proper submodule, and a module of the original vertex algebra will only stay a module of the quotient if whatever you quotient by acts trivially on it, right? And that's very hard to achieve. This means a homomorphic image of a true quotient, a non-trivial quotient of an affine vertex algebra has substantially less modules. And the drawback is it's very hard to classify. But and that's then what the whole business is about. You are interested in the exceptional set of levels because there you have a non-trivial simple quotient. Its representation theory is quite restricted because you now have to classify modules of the affine Lie algebra that have the property that the ideal you quotient by acts trivially on them, and then you have to go on. And my eventual goal of the whole week is to explain how this goes in the case of SL2, because and you will see SL2 is already enormously hard. But already one thing that is kind of fantastic, think about representations of the finite dimensional Lie algebra SL2. And I will actually be very explicit about those representations in this afternoon. So you all know finite dimensional representations. You have a simple finite dimensional representation of each possible dimension. You all learned that pretty early in a Lie theory class, in a Lie algebra class. You know that tensor products can be written down in a very explicit formula, no problem. Are these all modules? Well, by no means these are all modules, but you have a two-parameter family of infinite dimensional modules. What's the tensor product of two such modules? We can easily compute that. That's only something in the completion of the category. It's an infinite sum of modules. So it's already, in many respects, badly behaved. And so that means a priori there's no hope to get. I mean, so you should say it. Think about it as the largest or large representation categories already for SL2 are not really nicely behaved under tensor products. So there's not necessarily a huge hope that this will become nice for vertex algebras. Miraculously, it turns out they become actually really nice. So and that's where I want to go. Okay.
Is there a notion of a semi-simple vertex operator algebra? Like in Lie theory, if the modules are all simple or semi-simple.
Yeah. Yeah. We want to go. Is that correct?
Sorry.
But why don't you ask that question at the beginning of next lecture,
Yes.
and I will continue exactly here. Okay.